Alright, so in this short clip, we're going to be looking at the nucleophilic addition mechanism. Alright, so we're going to be looking at nucleophilic addition. You just write that there. Nucleophilic addition. And within the CAPE syllabus, what we generally look at under these reactions are the reactions of the carbonyl compounds. Right? And we generally look at it through the creation of the cyanide ion. Alright? So let's just have a brief look at how this mechanism occurs. So stepwise, we'd have step 1 first. So step 1, I would recommend to everyone that they form the nucleophile, right? So remember that nucleophile is a substance that bears the free pairs of electrons, right? So I would generally recommend to everyone that they actually start with that first. Okay, so start with the preparation of your nucleophile before you really do anything else. All right, if the preparation of nucleophile is there, right? So let's look at this. Hydrogen cyanide, right, in the presence of water in itself, right? Specifically, we're going to be reacting with the hydrogen ion to produce hydrogen cyanide and sodium ions. All right, and within this case now, we would know that the hydrogen cyanide would actually decompose into hydrogen ions and cyanide ions, all right, and ions. Okay, so this is the creation of our nucleophile here. Now let's look at the species. So if we have a species like this, all right, let me just draw it like this actually. All right, looking at a species like this, this is what you would call formaldehyde, all right? Or let me just add another group to it, all right? So ethanol is here, all right? Ethanol. So the reaction of ethanol with the nucleophile specifically now. Before we get to that, we have to have the creation of some amount of charge distribution within the molecule. So in this case now we know, let me just add in this. We know that oxygen is more electronegative than carbon within this bond here, right? And note that the double bond is a region of high electron density as well. So electrons are going to be moving towards oxygen in this bond, creating a polar bond. So we're going to have a slightly negative charge here and a slightly positive charge here on the molecule. All right, so we're going to have a dipole being set up. All right, so let's just draw the dipole arrow. We have a dipole being set up. Now this will create a slightly positive region here in which nucleophiles will attack, because nucleophiles are attracted to positive charge. So on the slightly positive carbon under here, we're going to have nucleophilic attack. So we're going to have this cyanide ion here attacking. And this will in turn push electrons from the double bond and send them onto oxygen. All right. So what will happen here now? We're going to actually break the double bond in order to add in the cyanide in this nucleophilic attack. Okay. So what is the result of this? We're going to end up with something that looks like this. This looks weird, so let me just draw it like this and draw the hydrogen going into the back actually. All right. Give it a second. All right, so we have the R group here being connected, and then we have the hydrogen going through these movements, right, into the back. And what we're gonna have here is our cyanide. All right, so up here now we're going to have the oxygen. All right, so but remember that the double bond is broken. Remember that this double bond was broken. All right, So that means that all these electrons will now be on oxygen. Note that there's a full head arrow being used, right? So that implies that 2 electrons moved. In the beginning, oxygen had 2 lone pairs. Now it has 3 lone pairs, all right? Looking at that, oxygen is fine with the 2 lone pairs, it's stable there. But oxygen with the 3 lone pairs now will bear a negative charge. And we know that this is not stable. But guess what else now? We have hydrogen ions in the solution from the dissociation of hydrogen cyanide. So if hydrogen ions are there, we're going to have them acting as an electrophile, engaging in some amount of electrophilic attack. So one of the lone pairs here will actually form a dative covalent bond with the hydrogen ion with a proton here, and we're going to have this being the product, all right? So we're gonna have, let me just draw back the general structure that I have here. Hashed lines going back for the net hydrogen, our group, and we're gonna have our cyanide group down there, and we're gonna have an alcohol group up here. All right, so that is what we're gonna have as a result. So this is the final product here. Okay, so step 1 here would be the production of your nucleophile. Step 2 is usually just looking at the creation of your dipole, creation of the areas or the regions of partial charge that your nucleophile or electrophile would attack, right? Step 2 is really about showing, well, step 3 is really about showing the breakage of the bond, right? So step 3 is really showing this breakage of the bond and the formation of the negative charge concentration on the oxygen, as well as the relationship between the oxygen on the molecule and the aqueous protons, right? So there will be some amount of electrophilic attack. And then step 4 is just looking at our final product, okay? So that's really how it works. So that's really the nucleophilic addition. Why is it nucleophilic addition, right? A lot of persons have the question, why in this case we have a nucleophile adding here and we also have an electrophile adding here. We name the mechanism based on what adds first. So the first thing to be added is a nucleophile. Therefore, it's a nucleophilic addition, not an electrophilic addition, right? So that's how it works. So step 1, creation of our nucleophile. Step 2, looking at the polarity with the bond and looking at the nucleophilic attack. Step 3, looking at the bond being broken and the electrophilic attack and step 4, writing our final product. So that is it for nucleophilic addition.